This next chapter introduces a new concept, or concepts, I should say, of impulse and momentum. We're going to talk specifically linear momentum. When we talk about rotational motion, we'll talk about angular momentum, so spinning. So this concept we typically apply for what we call impulsive forces. If I throw a ball or even drop a ball, for example, if I have a ball, I release it from rest, I know it speeds up faster and faster as it heads towards the ground. Right before it hits the ground is when it would be traveling fastest, but when it hits the ground exerts an additional force on it, or a new external force. The force that the ground exerts on this ball will cause its direction to change, and the ball will start bouncing back up. Now, how fast the ball bounces off the floor and how high it can go after bouncing depends upon the materials of the ball and the floor. A really hard ball, like if you had a billiard ball, a ball that you play pool with, that would, well, I guess I shouldn't say that. I wouldn't expect that to bounce as high as something that's like a rubber bouncy ball, one that's designed specifically to bounce. It certainly would bounce, mind you. But now that I think about it, of course, I don't go around dropping billiard balls on the floor, so I don't know how high it would bounce. Ultimately, when we talk about impulsive forces, in a situation like this, we're talking about the normal force. The force the floor exerts on the ball, thus causing it to change direction and bounce back up. This force is applied for a very short time. That's one of the reasons we use this word impulsive. Just something that happens really quick. The force certainly has a large effect on the ball because the ball was traveling down pretty fast and now it travels up. But that change in direction happens pretty quickly. So ultimately, in this specific situation, we're looking at just the very small time frame that represents the collision between the ball and the floor, while those two are in contact, which is, again, a very short time. But we know the force that the floor applies is what is ultimately responsible for that change in direction. So there's a new acceleration. That acceleration causes a change in velocity. If we were to graph, even just trying to estimate a graph of the force that the floor was applying versus time, it would likely look, that's a little too sharp, but something like a bell curve. Probably not perfectly, but somewhat something along those lines. The force would not be constant because of that motion of the ball itself, or I suppose it could be constant. It depends upon how easily the ball is deformed and compressed. Where my mind's going with that is I love to play racquetball. So a racquetball is hollow, and the material it's made of is a rubber of some sort, and it's very easily deformed. So when a racquetball hits a wall, you would need total slow motion capture to see it. The ball itself literally smashes. It becomes smaller. That's not something we can see without videotaping in slow motion, but the ball itself deforms, but then as it pops back out, it reaches again its original shape. We say the material of this racquetball is elastic, just like an elastic band, a rubber band. I pull it out, I let go, it snaps back to its original shape, assuming, of course, I'm not breaking it in the process. So depending upon the material the object is made of, it may deform, it may not, but in either case, there's some sort of impulsive force acting over some period of time that is causing this change in motion. So if we remember back, Newton's second law tells us that the net force on an object, or system really, is the mass of that object or system times its acceleration. So we've solved problems using Newton's laws. We can draw a free body diagram, but what we're wanting to do is come and look at these situations that we're defining as these impulsive forces. So something like a collision. It doesn't need to be the ball with the floor. It could be like a fender bender, a car rear-ending another car, or my favorite, it was a stupid part on mine. I was backing up in my friend's driveway and didn't look to notice there was another car in the driveway, and I backed right into him. That was awesome. Of course, not really. But again, my motion, as soon as the cars were physically in contact, of course, there was a change, an impulsive force that in turn affected my motion and also, I'm sure, made the other car jiggle a little bit in place. It felt that force. What we're going to do is we're going to make a new relationship in here. If you remember, acceleration is the rate at which the velocity is changing. So it is the derivative of the velocity as a function of time. If we bring dt to the other side, I'm going to be lazy and lose my vector signs, but force is a vector, acceleration's a vector, velocity is a vector, so just reminder, vectors are here again. If I bring dt to the other side and integrate both sides, we call this an impulse. That's the physics definition. Some force applied over this small time frame is called impulse. But we can also, on the right side, if we integrate the mass with respect to velocity, then that is also impulse. The symbol our author uses for impulse is a capital J. Why? I don't know. So we can calculate impulse by integrating the force that is acting in that small time frame, like with the ball bouncing off the floor, the force that the floor is exerting over the time it is exerting it, which if we go back to the graph over here on the left, that would represent the area under this curve. That is one way to calculate the impulse. But we can also calculate the impulse. We're going to go ahead and only look at situations where mass is constant. That does not have to be the case in real everyday life. Like if we think of a rocket being launched into space, the mass is changing because the fuel is being used up. I mean, I suppose we could say that's true for our car as well. As we drive, the farther and farther we drive, the more gasoline we've used up. But for our intents and purposes, we're going to look at situations where mass is constant. This integration is with respect to velocity, meaning velocity is our variable. That means if I integrate m dv, my limits of integration need to be lower limit v initial, so initial velocity, upper limit final velocity. In the force versus time, my limits would be a t initial to a t final. In the assumption of mass being constant, I'm just going to get mass times a v, evaluating this between some v initial and v final. And that v is a vector, so I didn't drop my laziness of vector notation very long. We can say the impulse is equal to this quantity of mass times velocity at a final moment in time minus mass times velocity at an initial moment in time. What we mean by final and initial, if we come back to this example of the ball hitting the floor, final means right immediately, as it leaves the floor. So right as the force of the floor leaves. So when the ball is no longer in contact with the floor. Initial, I mean this impact velocity, that split second before it hits the floor. So ultimately, when we're talking about impulse, if we're saying the impulse on the ball from the floor, we could calculate that if we knew the mass of the ball, the velocity of the ball upwards, that right as it's leaving the floor, and the velocity of the ball downwards at that split second before hitting the floor. That would be one way to calculate it. And the other way to calculate it, well, we could go ahead and find the area under a curve if we had that graphed, or we can think in average terms. If we were to talk about the average force the floor applied and multiply that by the length of time the ball was in contact with the floor, that too would allow us to calculate impulse. So we have two equations. Both of these would allow us to calculate impulse. Why I would choose one over the other depends purely on what information I have or what information I am being asked about. So that's how I would choose. But either way works. Now, this quantity of m times velocity, this vector, this is called linear momentum. Because we don't know any other type, if we've not taken physics before this semester, we often refer to it simply as momentum. Though technically it's specifically due to this linear motion. We are going to use a lowercase p to represent linear momentum. So this equation up here for impulse, technically, we could say was final momentum minus initial momentum, or the impulse was the change in momentum. So this is another way of relating forces to motion, but it's limited in its application. We're going to talk about a conservation of momentum, but we cannot apply it to every single problem we ever see like we did with energy. So we're going to walk through and talk about when momentum is conserved. We'll look at some problems looking and solving for just impulse or just momentum, and then also the conservation of momentum. Now, one big thing, momentum is a vector. We kind of get lulled into a false sense of security because energy, we haven't had to worry about vectors quite so much. We didn't have to worry about pointing to the right versus the left, other than figuring out if work was positive or negative. Momentum is a vector, which means we have to write it in terms of x and y components and work with those components to do calculations, which is fine. We know how to do that. We just have to often refresh our memory at this point. Now, really quickly, linear momentum has units of kilograms from the mass times meters per second. But this is also a Newton times a second. If you come back to this equation for impulse up here, if I can calculate impulse either by force times time or change in momentum, those two equations have to give me the same units because impulse has specific units. Which way we write our units doesn't ultimately matter. So either way is appropriate, but I wanted to introduce that to you. We don't have a special name for kilograms times meters per second. So we don't have a different name for it other than newtons times seconds. So we'll continue doing some examples and some concepts and move along with this topic as well.